So once again, we're still trying to understand this set Fi, which is ways to tile a 2x I plate with 2x1 Lego bricks. The way we're going to understand it now, the final approach that we're going to use, is with what's called a generating function. And we'll learn about these much more in the end of the semester. And we'll learn to do a lot of manipulation of these. But generating functions, the important things to remember are that they don't generate anything, and we don't want to think of them as functions. What is the generating function for this guy? It's f of x. X is going to be a formal parameter because I'm going to make a formal power series. This is just going to be the sum, I greater than or equal to 0, f of I, x to the I. We could start the indexing set here at 1 if we wanted to, but it's easy enough to put it at 0 and add the convention that f of 0 is 0 for this sequence. Sometimes you'll see a Laurent series, so you're going to let I be an integer. But this is the usual form for the generating function. This is called an ordinary generating function, and we'll learn more about those as we go. The idea is that it's just a compact way to hold all of the information for these coefficients into one function. So we're going to find a closed form for the generating function. It's not always possible to do, but in this particular case it is. The main thing that we're going to use, the main tool that we're going to use for manipulating the generating function to begin with is the recurrence relationship that we found. So the recurrence relationship, I'll remind you again, this is the Fibonacci recurrence. And our initial conditions are, of course, important. So maybe I'll write those down as well. We're going to have we have a convention f of 0 is 0, and then we have the initial conditions f of 1 is 1, and f of 2 is 2. So that's how we're going to start it off. Now, when we do our manipulation, what we do is we expand out the generating function by peeling off the terms that we need. So the first term is going to be 0, x to the 0. So that's just 0. We won't write that. The next term is 1, x to the 1. And then we've got the rest of the terms. So this is going to be the sum I greater than or equal to 2 of f of I x to the I. Now what's the point of this? Well, now the recurrence relationship kicks in, so we can use this recurrence. And we write this as x plus the sum I greater than or equal to 2 of f of I minus 1, x to the I plus f of I minus 2, x to the I. So I've distributed that in. And now the point is up to just factoring out 1x here and 2x's here, this is exactly this generating function once again. So this is equal to x plus, I need to factor out 1x here, and I need to factor out 2x's here. And now I have no more summations. So now I can solve for f of x, and this is a fairly easy one to solve for. You just get everything to the side, factor it on. You've got an x left over, and then I need to divide by 1 minus x squared. And that's a closed formula for my generating function. So now I have a compact way to keep all of the information in one place. If I want to put this on a computer, I can do that, and it can spit out what is the coefficient of x to the 108, and then I'll know what the 108th Fibonacci number is. Now, if I want an exact formula that avoids me having to actually manipulate this function, I can still get it from here, and that's one of the beauties of generating functions. The way that we're going to begin, just given the nature of this generating function, is with a basic tool from Calc 2, partial fractions. So remember, we have this beautiful thing called partial fractions. And it's going to allow us to simplify it as a sum of simpler denominators that we can manipulate. Partial fractions. So what we want to do is we want to write 1 minus x squared as 1 minus alpha x, 1 minus beta x. We need to factor it in this way, and it's not too hard to plug in the quadratic formula here, and we're going to see that, let's say, alpha is going to be 1 plus the square root of 5 over 2, and beta is equal to 1 minus the square root of 5 over 2. Okay, great. So that means that we can rewrite this now using our classic partial fractions expansion. We have that x over 1 minus x squared is equal to some constant over 1 minus alpha x plus some constant over 1 minus beta x. And of course, the way we're going to solve this is just getting these denominators in a common form, which will be this form, and this is going to be a times 1 minus beta x plus b 1 minus alpha x. A good reminder for when you teach calculus, you do have a system of equations. That is not the most efficient way to solve this. Just plug in x is 1 over beta, plug in x is 1 over alpha, and then you can solve for a and b. And what you'll find is that a is going to equal 1 over root 5, and b is equal to minus 1 over root 5. So what does that give us? We come back to f here. Now we can rewrite it like this. F of x is more efficiently written as 1 over root 5. I'm just factoring this out of both of them. 1 over 1 minus alpha x minus 1 over 1 minus beta x, where alpha and beta are these roots that we saw up here. And now what does this get us? Well, let's expand this back out in a generating function form. Remember, 1 over 1 minus x is just the sum x to the I. So this is equal to 1 over the square root of 5. This is the sum I greater than or equal to 0 of alpha to the n, x to the n, plus, okay, maybe not plus, minus the sum of I greater than or equal to 0, beta to the n, x to the n, which now if we combine terms, this tells us a closed formula for f of I. It's going to equal 1 over the square root of 5, alpha to the n minus beta to the n. And that's it. So now we have a closed formula for the Fibonacci numbers. This doesn't look like it's going to be an integer, right? We have 1 over root 5. But the alpha and betas also have these root 5s, and you can check that it does. In fact, it is going to telescope and cancel the terms. And if you want to compute the 108th Fibonacci number, this is maybe the most efficient way to do it. So now we have a complete answer to this set and understanding this family of sets, in particular understanding their cardinalities. We have a recurrence relation that we derived by doing examples. We asymptotically knew that it grew like an exponential, and now we have a closed form for the solution. And if we want to do other fancy things with it, we might come back and use this generating function and use generating function techniques to do more sophisticated things later. So that's it. That sums up our How to Count lecture series. So next time we'll dive into more examples and we'll go slowly through these different techniques that we're learning to see how they apply in different situations.